All right, hello everyone. Welcome back to Blueprint 101. We're on Section 3, Unit 1, Understanding Engineering Drawings. Before we get to the PowerPoint presentation, I just wanted to take a minute. Anytime you're struggling with finding the info, maybe it's not exactly in the book, you want to be able to find it. Remember, we have the largest library in the world right on the internet, okay? Now, one of the things that's going to help you be successful is figuring out what's good information and what's bad information. So here's a Wikipedia one, and I know people have their own views about Wikipedia. We're not going to get into that. But this is just, I just typed in machining, drawing, and symbols. So it brought up here engineering, drawing, abbreviations, and symbols. So we want to walk through this for a minute. And we're just going to talk about a couple things here. So as you're working through this chapter, feel free to Google the abbreviations. So a big one right here is going to be AISI, the American Iron and Steel Institute. Okay, it's the acronym commonly seen as a prefix for steel grades. So for example, AISI 4140. SAE steel grade system was formerly a joint AISI SAE system. So you'll see it quite often. It might be an AISI number or an SAE number, okay? Another big one walking through here, you know, ANN, you see this on the print, so that means anneal, okay? Let's walk through a couple more. ASME. This is a large one, American Society of Mechanical Engineers, one of the governing bodies in a lot of fabrication, design structures. Burnell hardness number, CAD, CAM, so forth. So here's the first example of an actual symbol. It's not in bold colors, it's somewhat shaded, so let me see if I can zoom in here and show you. So it's the center mark, okay? It's an up and down symbol showing that it's a center mark. I'm going to go ahead and just leave it kind of zoomed in here and we'll walk through this, okay? So as we get down here, now we have counterbore, countersink symbols. Okay, so there's our counterbore. Right below it is our countersink, the V-notch looking one. Come down further, here's the depth, how deep you go, how far down it may be. So the counterbore, you may see a counterbore with the depth symbol showing you how deep it should be on the counterbore versus the rest of the way, okay? The diameter symbol does not have it here. It is simply a circle with a cross drawn through it. And on your blueprint, going through Blackboard, you should be able to, I'll upload this and mash it, or do what we call a mashup on the Blackboard, to where you'll be able to pull this up, look through the symbols yourself, come through and be familiar with them. Because this doesn't have all the symbols, but it's a good place to start, all right? Okay, so I will zoom this back out. I am not the only one here today. Dan Holland is with us as well. We're going to be walking through some blueprints, talking about some things that you might see and catch. Two eyes are better than one, especially when it's looking at a set of blueprints. So, Section 3, Chapter 1, starts out in the Precision Machining Technology book, roughly page 202. Understanding drawings. Okay, the importance of engineering drawings. They show sizes, shapes, and features produced in a standard format. Machinists must be able to read them. Welders, trades, pretty much anybody that's going to be designing or building to a blueprint, you need to understand how to read the blueprint, the title block, understand the different views, what you're seeing in it, and be able to interpret from it what you need to get out of the part and how to process that part, okay? Components of engineering drawings are the title block, orthographic projections, and line types. So here's an example. Start with here, shows us in large format. The title block is this bottom section here. It's going to give you the main information, okay? We're going to break it down here in a minute and talk more about it. But just relative to the entire print, here's our title block of an engineering drawing or print. B is the revision block up top. Okay, sometimes you'll see certain things, you'll see a tolerance block up top. It doesn't always have to be up top. It can be down here as well. And then down here, looking through this, the bill of materials is the C, this top section right here. Okay. Certain cases you may have, I believe in this one, we do have bronze or steel material for the bushing. Number 2 doesn't give a specification on, that's just a hex head bolt, so it'll tell you what grade of bolt it is. Number 1, the actual block itself is going to be cold rolled steel or a mild steel, okay, CRS. So this is where you really start to need to know how to be able to interpret the abbreviations within machine drawings and so forth. Okay, cold rolled steel is CRS, hot rolled steel would be HRS, and so forth. Okay, so we talked about orthographic projections. We backed up here for 1 minute. We're going to read through the title block a little better. Not exactly happy with what they left it at here. Okay? So we're going to see if we can find a title block. This one seems fairly easy to read. Okay, so we're going to come through, we're going to zoom in on it, talk about it piece by piece. So to start with, this is the machining skills level 1, job duty 2.2, manual operation / layout. Okay, but this may have a completely different title block for it. Say it's the Ford rocker arm part for Ford engine, 460 engine. Okay, so it's gonna tell you in detail what that part goes to, and so forth. First of all is the designer. It's going to tell you who drew it up, what date it was drawn, the material. So here's cold rolled steel or a mild steel. Sometimes you might see it as CRS. If you have several different components with it, you'll usually have a bill of materials. This one only has one component, so there's only one set here. A lot of our prints you're going to see defined as CRS or HRS or AL aluminum, and then you're going to need to go to the AISI number and figure out what type of and what grade is it, okay? So for example, if it's 1018 CRS, then we know it's cold rolled steel, 18.18% carbon out of the 10 series of steel and so forth, okay? A lot of times it will give you the actual grade of steel instead of just telling you cold rolled steel or mild rolled steel, all right? Over here to the section is going to give you your tolerances. So this one is giving us, we're going to draw this up because it doesn't really help us out too much, okay? We'll talk about these tolerances here in a second. We'll define them a little better. Down here's the scale, and it says full. So we're just going to amplify it here. Okay? So it'll go up, across, down. Okay. So tolerances. What it shows us is X is a 0.002. XX is point, it's hard for me to see, I've been looking at it so long. 0.015. Down here I can see the angles are 0.1 degree. Okay, and then 3 place X, 0, 0, 5 thousandths. Okay, down here it also tells you fractions are to a 1/64th tolerance. All right, real quick. We're looking at this section up here. I can't see, I do not see any fractions whatsoever. However, let's look here. The bigger, larger numbers, say 3 to 60, sorry, 3 inch or a 6 inch, they can be held within a 1/4 spec as well. They're only at 1 decimal place. However, that's not very critical. So in this case, they would fall underneath the 1/64th, which is 15 thousandths, roughly. Correct, Dan?
That's correct.
We went on the other one, we broke down the decimal points, we talked about it, we showed you where they were. So here's our tolerance sheet over here. So now let's talk about this a little bit better. Okay? So if we have a measurement that we're running at 3 thousandths and we want to run, say we're at 1.412 inches, okay? Let's do another 1.250, 32 degrees. Should be able to work from that. One and 61/64. Okay? So as we define tolerances here, we're looking over at our right-hand sheet. I got something wrong on that? Because I'm showing one place I have to hold within 1,000. Doesn't seem quite right to me. It's hard to see that, isn't it?
Does that say 0.0032?
It does say 3. So, here's my correction. 32. Okay? 32 thousandths of an inch. So real quick, the other day, we walked through this, half of that, half of that again, half of this again, okay? So just by doing some simple, quick math, what we did is we just broke down fractions into decimal places. We did a quarter, we know it's 0.250, took half of that, now we're at 125, half of that again, and 625, 1/32 here, And again, we get into 1/64, which is 0.015625, if I remember right. So, just a quick way, if you're looking through, put 032, what does that mean? Basically, what that means is we're going to be within 1/32 of an inch on a single place. Okay? Anything you want to put in there, Dan?
Nothing yet.
Nothing yet? Okay, so let me back up here so we can see our tolerances over here. Left-hand side in this portion, okay? So first things first, our tolerances are fractions, 1/64. See if it tells us a plus and a minus. So in this case, we would be allowed our maximum material condition and least material condition. We're going to add 1/64 from each one. So we would be at 1/62/64, 1 and 60/64 of an inch. Okay? Naturally, those are improper fractions. We could break them down into smaller detail. However, you're understanding, you're getting what I'm going for here. Okay? So the next one, we've got 3 decimal places. 1, 2, 3. Okay. So now we're going to come over here. We're showing 3 decimal places, so our tolerance is going to be 5/1000ths of an inch. Say it's a plus or minus. It didn't specify. We're just going to go with plus or minus to make our point. So again, our max material condition as well. Sorry, I just want to make sure I'm making that right. Is it MMC or MML? MMC and LMC, yes. Okay. I thought I was right, but I wanted to make sure. I can make mistakes as well. So max material condition, we're going to add 5/1000ths to it. So 1.417. Least material, we're going to subtract 5 from it. So now we're at 1.407. Combined, we have 10/1000ths tolerance. Okay? That we're allowed. Accumulated, top and bottom, both sides. Down here on this one, I erased the 0 so we can talk about the 2 places. 1, 2. So now we are allowed plus or minus 15/1000ths. So in this case, MMC is going to be equal to 125 plus 15. So we're at 1.40. LMC is going to be, subtract 15 from that, 1.10. So 15 times 2 is 30. Just to make sure, we have 300,000ths in there. Okay? That's not what it says though, is it? No, it's not. What this is showing us is 2 places, but it's giving us 3 places to deal with. Okay? So this is sometimes where it can be tricky with a double place, 2 position versus 3 position. So what we were going off of was completely wrong. So now we want to add that 0. It's 2 places, but we're still going to add the 0, but I'm going to make it like a kind of what I call a soft 0. Okay, I'm still going to erase it, but I put it there so it helped me do my math. All right. So over here, 2 positions. We're still going to 3 positions in decimal. Okay. So we're at 1/250 plus or minus. Our max material condition is going to be 1.265. Our least material condition is going to be 1.235. So now we're 30 thousandths difference. Remember to keep in mind where the decimal point is. We're at 30 thousandths instead of 300 thousandths. Even though it's showing 2 decimal places, we still have to convert it to do the 3 positions. Okay? So that's a totally different story than what we were running earlier. We did just off of the 3, or the 2, we had 1.40 and 1.10. It's a big difference. Okay? So just remember to not just get caught up in, well, it's only 2 positions, so I'm only going 2 positions. Look at how many positions your tolerance is. All right? So 32 degrees, max material condition, same thing, 33, 31 degrees. Okay? When you get into more advanced prints, it may bring you down into degrees, seconds, degrees, minutes, and then even seconds, quite possibly. Okay? Okay. Let's go back to our PowerPoint title block. The scale. In the previous chapter, we talked about the scale. I'm not really going to cover it again, but remember whether it's 1 to 2 or 2 to 1. Depends on the size, okay? In this case, the scale is full. We have every dimension we need. We don't need to draw off the print itself in order to accommodate it. But if it's drawn, so for example, we can't draw a large mall complex on a little bitty print to scale. I mean, it would take tremendous amounts of paper. So we will back it down maybe times to the thousandths of a measurement, so 1 to 1,000 and so forth. All right, on residential prints, large scale items, but on smaller parts, we do the exact opposite. We will amplify it because at the same time, we cannot take a 1/2 inch total part and draw it to where we can see. Okay, so we might be inverted again. I showed you in the last section of like a 10 to a 1 scale. So if it was 1 inch part, we're going to draw it as 10 inches so we can see the detailed views within it. All right? Okay. I think that was a pretty good breakdown of the title block. You'll get some experience going through the title block more throughout this chapter. I want to go ahead and back up to where we were, and we'll start talking about the orthographic projections. Okay? So the orthographic projection uses different views to show three objects in one view. So we're now on page 204. Follow along on that left-hand column. Top paragraph, you'll see in italics orthographic projection. Different views to show 3-dimensional objects in 2 dimensions. So 1